Welcome to this new video. In this video we'll cover NAND gate by NOT and AND gate. So first of all you should know what is a NAND gate. So let's start from the beginning. So in the Verilog section we are going to learn about structural modeling. So I have made one separate video where I have shown there are 4 types of modeling, but I have not covered the structural modeling and the mixed modeling. So here I am going to share the idea of structural modeling for beginners. So for this structural modeling I am taking an example of a NAND gate. We will create the NAND gate by the structural modeling style, but for that we need some instructions. These are module input, output, assign, always, begin, if, end and end module. So these instructions are needed, so it's better to be said as keywords rather than instruction. Let me change this: keywords needed. Yeah, so this is what. So let's begin first. So as you know, as for NOT gate, the input is totally inverted. So we also say that it is an inverter. So when I am giving an input of 0, I will get 1. When I am giving input of 1, I will get 0. And this gate is one of the best and useful basic gate circuit, which has only one input port and one output port. So for the next one, it is a NAND gate. NAND gate is basically combination of our AND gate and a NOT. That's why I have covered the NOT here. So here you can see that this is the table of the NAND gate, which says truth table of NAND gate. So truth table, it is showing that when it is 0 0 I will get 1, 0 1 I will get 1, 1 0 I will get again 1. But when it is both high, both the inputs are high, 1 1 I will get 0. So this is what we need in our final output. But for that we need to learn about the structural method. So for the structural method, let me first open the model sim software. So I have already opened in my background. So here I will show you that I have already created some programs. This is the NOT behavioral program. So there will be definitely a separate video for the NOT behavioral program, but this is created, so you can see the program here also. And in the last video I have shown you how to create behavioral programming. So the behavioral programming style was for the OR gate I used in the last video, but this is written for the NOT gate and it is in a behavioral modeling style. And I have already created in the first video this AND_gate where the installation was done in that video. So that was the AND gate creation and it was by data flow modeling style. So this is data flow. So this AND gate.b, which is in a data flow modeling style, and this not behave BEHP. So this is another file which is written in a behavioral modeling style. So these two will be used today for the third method of our modeling style, that is the structural modeling style, right? So let's begin. So for the first time you must have to think about this one, that the NAND gate is internally looped like this one, that the inputs of the two NAND gates will be definitely the inputs of an AND gate, and the output of the AND gate is input of the NOT gate, and the output of the NOT gate is basically our desired output, that is our NAND gate output. So to make that, you can think that I have taken a separate AND gate, I have taken a separate NOT gate. Now I have one where. I am naming this where as W1. So be careful that I am naming the where as W1. The name of the where cannot be like 1W or 1M or 2M or nothing, because the name must be start with the alphabet, and it can contain the numerical letters, that is 1 to 0. So this it can contain, but you have to start with any alphabet. Okay, so that is the naming sequence which is used in Verilog. So this is very much important, else you will get error. So this is what I have created, and I have taken in my left hand side this is my AND gate, and the right hand side this is my NOT gate. Now I want to have two input ports in my NAND gate, P and Q, and one output port in my NAND gate, OP. So OP is the name of the output port. Okay, so OP is single port, the output port. So P will be similar to the B port, Q will be similar to the A port. As I said that the input of our NAND gate are basically input of the AND gate, so that's why the input P and Q are respectively B and A here. So you can do the other thing, that P and Q are respectively A and B, you can do that also. So it's totally depending on you. And next in the output, that is the Y here in the AND gate. So in the output I will join this W1 wire one end, and in the another end it will be connected to the input of the NOT gate. So the input of the NOT gate is named as X, and output of the NOT gate is named as Y. So why I am naming in this order? Because if I go to this program, you can see that the input of this NOT gate is X by this line. You please follow. So input of this NOT gate is X, and the output of this NOT gate is Y. So that's why I have written this, that the input is X and the output is Y. So it's time to build the structural. So for the structural modeling, I will open my already written structural code. So here you can see that the module is NAND underscore struct. So this is the name given to the module. This is NAND gate, and it is written in a structural modeling style. So that's why it's I have preferred this name. So it does not mean that you have to give the same name, so you can change it also. So and this is the input P and Q for the structurally written NAND gate input ports. Okay, so the input ports are named as P and Q. So go to the PPT again, you can see that the input ports I have said that it is P and Q, P and Q. So that's why I have written it here, and the output is OP, and here also the output is OP. That's why I have described in this figure. So now it's time to join, it's time to connect. So I'm taking one wire also. So I'm taking the wire, and it is wire W1. Now I am taking this AND underscore gate and 1. So AND 1, it may be anything. You can give the name as X1, you can give as unit 1, or you can say as gate 1. Anything you can say. Even you can give your own name, like I am giving my name. So you can give anything. So this is the AND underscore gate. But how we found this AND underscore gate? So let's say, let it be AND 1, what it was. So I am getting this name AND gate from this one, this AND gate dot v. It has the module name AND underscore gate, right? So if I change here, right, I am writing here AND underscore gate underscore module, and I am saving this. So this need to be changed here also. So I am changing here AND underscore gate underscore module. So whatever the module name is, it should be present here. So if I go to the NOT gate section, so it is the NOT underscore behavior, but the module name is NOT underscore gate. The file name is NOT underscore behp.v, but the module name is NOT underscore gate. So that's why I am using here NOT underscore gate. So please use the module name. Please don't take any consideration of your file name or anything like that. Okay, so please go for the module name. And here after NOT gate, I am again writing the unit name. That is, this is the NOT 1. This is the first NOT gate, so that's why I named it as NOT 1. You can name it anything. You can say it anything, just like the AND 1, right? So you can, but please be sure that this one is declared as AND1. So if you write here the same thing, that this is also AND1, so it will not work. So these two must be different. Okay, these two, this AND1 and not one are different, so that's why it is perfectly working. So dot x, why it is dot x, why it is dot a, I am going to clarify this now. So under this AND1 I have said that dot a, then under the parenthesis this is p. So p is the input port of this module. So this is the NAND structural module, it has p, so that's why this is written under the parenthesis, in between the parenthesis. And this dot a refers the AND gate module, this module's input. So I am going to this module again, and you can see that here the input is A and B. So what we have drawn in our figure, so A and B. So for the A I have to enter the Q, and for the B I have to enter the P, or you can change them also, right? So interchange them. So here if I follow the same figure, for the A I want to enter Q, so for that for the A I will enter Q, so for that I should write here Q, and for the B I should write P. So this Q and P are the input of this module, and A and B, that's why I have used dot. So this dot is referred that these A and B are for the AND gate module. And similarly the dot y was AND gates output, if you see that the output was y. And for me the output with the output of the AND gate I will connect W1 this wire. So if I go to the PPT again, you can see that I have mentioned here that this section of this W1 should be connected to the Y. So I have connected that W1 with the Y. Now for the NOT gate also, NOT gate has its one input X and output Y. So please go to the NOT behavioral code where I have written the program. So here you can find that the Y is output and it is register type, definitely, because I have written the code in behavioral, and in the X is the input, X is the input. So that's why I have written here dot X, and under the parenthesis, in between the parenthesis, I have written here this W1, because this W1 is one side connected with this output of the AND gate, and the W1 another side will be connected to the input of the NOT gate. So I think it's clear. So and then dot Y, and this dot Y is referring to the output of the NOT gate, and this is OP. So OP is the final output port of my NAND structural program, and I am saying end module. Okay, so that's it. Now it's time for us to Control S. So saved. Now these two are saying as question mark. So I can go for this and compile selected, and yeah, it is successfully compiled, and again for this compile selected. So both I have changed right now, so that's why the status changed to question mark. So now it is showing a tick mark and in green sign, so that's why I can go to the simulation panel. So I'm going to this library, under the work this module name will be present, this NAND_struct. So yeah, this is the NAND_struct, right? So right click and simulate. So when I'm clicking the simulate, then it is opening the simulation panel where the objects will be present. There will be an active window, and there will be the wave. So you can find that for me the wave is present here right now. Please follow my cursor. This is the object panel, and beside that this is the wave. So if I click here, I can get the wave. But if I don't have this window already open, so for that you have to go to the view and then click wave. So if I click the wave, it will definitely take some time to fit the screen in the right hand side. Finally it has fitted it in the right hand side, and now you have to go and make the cursor perfectly on your objects panel, and now right click, then add to wave signals in region. So this is what we have finally added the um, input and output ports in this wave simulation panel. So I have to mention the clock, so I am right clicking on each and every one and going to the clock, and let's set this to be 200. So the period of this will be 200. So by default it is set as nanosecond, so no need to change. Okay, and again clock, it's 100, so it is also by default set to nanosecond, no need to change. So if you have any query like whether it is in nanosecond or not, so you can find it from the console also, that you can see that it is 100. So 100 means by default the unit which is selected as nanosecond in the software, so that's why it is nanosecond in nanosecond format. And you can lift it as 1 US. 1 U means basically mu here, so that is a microsecond. So 1 microsecond means 1000 nanosecond, right? So that's why I can do this also. So I prefer everyone to do 1000 nanosecond, but there is no specific reason for that. So if I run the program and simulate, and so here you can find that W1 is also present, so you can remove that. So right clicking on W1, go to the edit, and instead of cut, copy, paste or anything, you should go for delete. So I have deleted this one successfully because we don't want the W1 status in at every time. So that is the desired output, which what you can see here. So is that desired? Yes. So let's check. So this is the NAND, OP is the NAND output port. So here the OP is 0 only when the inputs are both 1, and this one also inputs are both 1. For this 0 also inputs are both 1, and for any other combination of input it is always 1. It is saying always high. So this is the output, and let's check it with the truth table. So the truth table is also saying the same. With both A and B are 1, the A dot B bar, that is the NAND output, will be 0. So finally we have built our NAND gate in this Verilog program through structural modeling. So this was your first introduction to structural modeling. Definitely you may find somewhat problem or anything, so please reach out through our comment section or anything. And if you find any problem related to your Verilog model sim software, so for that you can also follow our installation video, and you can also comment it out right here. So if you are new, please subscribe, and please like and share with your friends and community with this video. So thank you.